I got it.
Hi, David. You said
All right, while I'm getting the slides pulled up. We have to have a talk. We talked about AI already once. And then the very next assignment, almost the simplest assignment that we're gonna have in this class. Half, 2/3 of you use ChatGPT to answer the questions. I told you it's really obvious. I told you, please don't do that. This is your one pass. If I have to start getting more strict about that and start giving zeros on assignments. For this one, I basically didn't mark down anybody for this. But I really don't want to have to go down that route. Don't do the work, you're not gonna pass this class. You can't use ChatGPT on every assignment. So please don't. All right? You will get more out of this class. And you will pass this class if you actually do the work yourself. I know that's not directed to everybody in here, but there's enough people that did that in this class that I would really want to make the point to everybody. Please don't do that anymore. All right. Let's see where I have a point open. Other than that, y'all did ask some good questions, at least. And in general, I think the oddly enough, it seems like there was a number of people used AI for parts of it, but not the entire thing. So at least you're trying on parts of it. So silver lining, let's just go for trying on all of it. Better to take a deduction on points than it is to get a 0 on the assignment. So we're going to do some more practice with conversions today. Random quiz questions. Somebody asked about Kelvin, which is a temperature scale called an absolute temperature. We're going to talk more about energy in the next week, so this will make a little bit more sense. But basically, temperature is kind of our macroscopic way of looking at the individual energy or the energy on average of the molecules moving around in a system. So on an absolute temperature scale like Kelvin, when you go down to 0 Kelvin, that would be equivalent to all motion stops. All of the particles stop moving completely when you hit 0 Kelvin. And the thing is, we can't really do that because there's no way to actually have a part of the universe separate from the rest of the universe. So even if we were actually able to cool something down all the way to 0 Kelvin, the second it got to 0 Kelvin and all molecular motion stopped, something bumps into it. And as soon as something bumps into it, it's moving again. So it's basically, we know that it exists. We can't in our universe actually reach 0 Kelvin. But it's not like infinity where it's this sort of like abstract concept. It is a real thing. It's just not possible to get there. Several people actually asked about using salt to melt ice and snow, and what's the difference between road salt and table salt? Basically, salt is a chemistry term. It's kind of an old school term for any ionic compound, which basically means that you've got a compound made up of a metal and a non-metal. When you do that, when you put an ionic compound and you dissolve it in water, what happens is it actually lowers the freezing point of that water. And so the difference between table salt and road salt are they're actually totally different compounds. They're both salts in that they're ionic compounds that have a metal and a non-metal as part of it, but they're totally different. Table salt is what? What is the chemical name for table salt? Anybody know? Sodium chloride. The road salt can be a variety of things. The best And then we don't actually use it on roads typically, especially not here in the basin, because it has environmental effects. But when you're trying to balance, choose what kind of ionic compound to melt ice, you want to go with something that's not going to ruin the environment that you're in, something that's relatively cheap, and also something that actually splits up into more pieces than sodium chloride. When we talk about ions in a couple of weeks, this will make more sense. But basically, some compounds have more pieces to them when they dissolve. And the more pieces you can get out of a compound, the more it's going to lower that freezing point. So calcium chloride gets used a lot for residential places, but I think that they're still using magnesium chloride. Is it magnesium chloride? I think it's magnesium chloride. It's usually what gets used on road salt. But basically, it's just about finding what's cheap that's not going to ruin the environment, but it's also going to be better than table salt. And then you just dump that on the roads, and it lowers the freezing point, so your ice melts even if it never gets above freezing. And somebody asked about, is the math in this course going to get more difficult, or is it all just review? I mean, it's kind of all just review. This class is less about teaching you new math and more about how to use the math you have in new ways. So that's where we're going to do a lot of algebra. We're going to do a lot of unit conversions. We're going to use unit conversions as a tool to answer lots of different types of work problems, like that problem on the quiz about how far can I go on on 2 tanks of gas, right? So we're going to do some stuff like that. The only math that wasn't on the math review that we're going to use is logs. We're going to talk about logs and exponential functions in a couple places, but more on a conceptual level. Basically, if you know what a log is and know where the button is on your calculator, that's all the math you're gonna have to do with logs. We're not gonna do much with algebra of logs or anything like that. I'll mention a couple of places where that gets used to derive some equations, but I won't make you do it yourself. So basically, if you can do algebra and you can do conversions, you can do all the math for this class. When you get to, when you take Gen Chem, it's more about writing your own algebra equations, which gets tricky. It turns out writing your own algebra equations is harder than solving algebra equations. And we basically have a whole year series where that's the trick that you're trying to learn, in addition to covering some of this other chemistry topics. But yeah, if you can do the math review, you're good. Just gotta learn how to use it in different ways. And then a whole bunch of you wanted to go through some practice of these conversions. Some common issues. Everybody did get a copy of this, right? Okay. One of the main things that I mentioned, but maybe I didn't emphasize it enough. Watch your capitalization. That's not millimeters. A significant number of you converted 15 millimeters into feet, as opposed to megameters. Capital M means it's mega. Like you said, it's a not insignificant chunk of you did that. It's easy to do. You're not used to paying attention to capitalization on units. We're gonna have to, because there's a difference between megameters and millimeters. In general, people struggled with the metric prefixes. I wrote out nano years for this one, but it's still hard to figure out how to use this conversion sheet to get there, right? So is a nano year smaller or larger than a year? Smaller. So, and I left this for example. This is straight off the conversion sheet, right? 10 to the minus 9 meters is 1 nanometer. That's what this multiplier means. And as I mentioned before, that actually means there's 2 ways of writing it. I don't like thinking in negative exponents if I can help it. So I can say that a very small chunk of a meter is one nanometer. I like to write it the other way around though. I say there's a whole bunch of nanometers as 1 meter. So you can write, we'll switch it to nano years instead of nanometers. You can write 10 to the minus 9 nano years equals, or sorry, years, eraser. 10 to the minus 9 years is 1 nano year. I flip it around and say 1 year is a whole bunch of nano years. Just for whatever reason, that's easier for my brain to process. I think when I hear nano, it's going to take a whole bunch of nano something to make one of that regular unit. It still has all that information right here though, right? It still has that multiplier listed. So this is still useful, but this is the conversion that I would use. They'll both give you the same number though. You're either going to be multiplying by a really small number or dividing by a really big number, which has the same net result. And so if we're trying to go 14 nano years into seconds, and then we can, first thing, if we get into regular years, we know all the conversions probably off the top of our head, but at the very least, we have our conversion sheet to do all of our standard time units, right? So first things first, we just want to go from nano years into regular years. 10 to the 9 nano years is 1 year. And then we can go 1 year into days, 365.24 days. And then we can say 1 day is 24 hours, 1 hour is 3,600 seconds. So this one took a couple steps. And the other common mistake that a lot of people made is rather than show all the units and write it all out like this, once you got to something you felt comfortable with, you just wrote the numbers without writing the units with it and without writing it as a conversion factor, which works until it doesn't. At least 3 of you multiplied by a number you were supposed to divide by at one point. So that's what this gets you, is it helps you not mix those up. Right? Because now I can say, okay, well, 1 day, 24 hours, finish writing it out. 1 hour, you can go to 60 minutes and then to 60 seconds, but we also have that one written right there already. So we can just say 1 hour is 3,600 seconds. And then by doing it this way, that makes sure that we keep everything on the right side of the dividing line. Right? We're not going to wind up dividing by something we're supposed to multiply by. And somebody else can follow your work and know what you did. It's not just about me being able to assign a grade, but there's going to be times when you have to do some math in the real world, not just in this class. You're going to have to do some math and you're going to have to show it to somebody and convince them that you did it right. If you don't show your units, you just have a bunch of scribbles and I multiplied by this number here. Like, how do you convince somebody you did it right? Even if you did, you need to be able to communicate it to other people. Right? And that's what the standard sort of notation in writing your units is going to get you. The ability to communicate with others, not just convince yourself you did it right or keep track for yourself. So always make sure you're writing units. In this class, you should not write a number without a unit. There are a couple exceptions to that, but few and far between. When you write a number, you should have a unit with it or some sort of context so that somebody reading knows what that number is. All right, so I think the answer came out to be 0.44 seconds. You did all the math right on this one. The other thing I want to emphasize is using these conversions. It doesn't have to be just these, but a number of you just made the assumption that a meter is 3 feet, which, I mean, it is, but that's only one sig fig. It's really 3.3 feet. Well, it's really 3.29 feet. Well, that's not an exact conversion, right? So if you're going to say a meter is 3 feet, that's only one sig fig. You only get to keep one sig fig at the end when you actually do the math. So if you stick to the conversions that are on here, one, that's one way to make sure that you're demonstrating you're not using ChatGPT. Because that was one of the dead giveaways, was that ChatGPT uses conversions that that aren't on this. And written in a very specific way that made it obvious where it came from. So stick to these. So you shouldn't be going megameters to meters directly to feet, because I don't think that there's a meters to feet conversion on here exactly, is there?
No, it's 6 centimeters.
There's a yard is 3 feet. You could go from megameters to kilometers to miles to feet. Or you could go from megameters to meters to centimeters to inches to feet. There's 2 different routes that'll both get you there. But they're both better than a meter is 3 feet. All right, any other questions on the quiz questions? Yeah.
On B, I assume that was fluid ounces, so I did fluid ounces.
Good, that's another thing actually that I was gonna talk about that I forgot about. How do you know ounces shows up here both under volume and under mass? How do you know which one to use?
Volume, because milliliters is.
But by looking at the context of the other units, we don't really have a whole lot of experience converting from a mass to a volume yet. That isn't one we're going to do. But if we're trying to end in volume, and this is all the information we have, we're going to want to assume that that's a volume as well. Otherwise, we're actually assuming a density. The reason that ounces gets used both as a mass, this is one of many reasons why the imperial unit system is trash. Ounces gets used the same for, as written the same for both fluid ounces and for mass. And it's assuming that you're talking about water, basically. It's using the density of water to say that 16 mass ounces is the same as 16 fluid ounces as long as you're talking about water.
So you actually could do 16.
If you assume that it's water, it has the same density of water. We don't want to make that assumption because I didn't tell you it's water. So in this case, we want to stick to everything as a volume. And so you just want to be paying attention to that. You have a direct conversion from ounces to quarts and quarts to liters, and liters you can get to milliliters. We don't have a direct conversion. If you started going the other way, if you started going from treating this like it was mass ounces, the only conversion we have there is to pounds, and then we're stuck in pounds and we can get to grams, but then how do we get from grams to milliliters without a density involved? So that's a good thing to pay attention to, is the context of the units too, because sometimes you won't necessarily have a number. A number will be written with units, and you have to figure out what that variable is based on the units that are written. So you do always want to be reading for context when we're talking about units too. Any other questions about the quiz? Okay. Get that out of the way. There we go. So, and just to reiterate, unless you're paying a lot of attention to your sig figs, there's really only a few conversions between metric and imperial. The one that we're going to come back to all the time because it's exact is centimeters to inches. 2.54 centimeters equals 1 inch. That's an exact conversion. Every other conversion between systems is approximate, meaning it's a measured number, meaning we've got to worry about sig figs. If you stick to only using exact conversions, the sig figs you end with is going to be the same as the sig figs you started with every time. If you use an approximate conversion in there somewhere, you need to remember that that approximate conversion is measured and that counts towards your sig figs. And so the easiest way to not have to worry about that is to use the exact conversions. So unfortunately, that also means if you want an exact conversion going from miles to kilometers, you can't just use this nifty conversion right here. if we want an exact conversion, we actually have to go miles to feet, feet to inches, inches to centimeters, centimeters to meters, meters to kilometers. And to get something that's gonna be approximately 1.609. So it's not always worth it, but if you have a lot of sig figs, it is. If we're trying to say, let's say 50.000 kilometers, I wanna go to miles. We could use this, but then our answer can only have 4 sig figs. If we wanna if we go to the trouble of measuring this out 50 kilometers all the way down to plus or minus a meter, that was a lot of work to measure that, right? We don't want to just round off that last decimal just because we were too lazy to go the long route to do our conversion. So we would wind up going 1 kilometer, 1,000 meters, 1 meter, 100 centimeters, 2.54 centimeters, 1 inch. 12 inches is 1 foot. 5,280 feet, 1 mile. So if you work your way through that, you should get something. These, if you multiply all these out together, somebody else asked a question about, are there any shortcuts for conversions? Well, yeah, depending on what you're doing, what you're trying to convert. If you take all of these and just multiply them all out, do the division and everything, you get 1.609 something. So you can condense your longer conversions into a 1-step conversion. If it's to your advantage to do so. Like, so if you're, I don't know, maybe you're working testing water quality in the Keys, you're looking at the quality of the lake water. And you have to do a conversion where you convert gallons into cubic meters. You could do that and I'm gonna teach you how to do that the long way in a second, but if you're doing that 5 times a day, every day for your job, you're gonna have a condensed conversion to do that. And that's fine too, you just have to pay attention to your sig figs and where it's rounded. The other piece to this means we don't actually have a good conversion for volumes to go from imperial into metric or vice versa. If we're trying to convert from volumes, I did give you a pretty good one here. There's 5 sig figs. That's usually going to be enough sig figs. But where did that number come from? Well, it came from by condensing a bunch of conversions that we're going to talk about here in a second. If we want an exact conversion between imperial units and metric units in volume, we still have to use 2.54 centimeters equals 1 inch. How's that going to work? Because that's a length, not a volume. What kind of units do we see for volume?
Gram, meters squared.
Meters squared, that's not a volume. Cubed, yeah, meters squared is area, right? Meters cubed is a volume. If I just said what is a volume, it's a space in 3 dimensions, it's enclosed, right? That volume really is length in 3 dimensions. If you think about finding the volume, what's the simplest object that you can find the volume of? Simplest shape. A cube, a square, not a square, cube. Because, and what is that gonna look like? Looks like a square in 3 dimensions, right? Now I want to find the volume of that cube. What is it? What's the formula for it? Length times width times height. if all of those are 1 foot. It's 1 foot by 1 foot by 1 foot. What's the volume?
1 foot cube.
1 foot cubed, 1 foot times 1 foot times 1 foot. If I wanna put that into centimeters instead. If I want the volume not to be in cubic feet, so volume is 1 cubic foot. If I want that in cubic centimeters instead. I can take 1 foot and I can convert it to centimeters, right? And I could do that 3 times. I can say, okay, well, 1 foot. And 1 foot is 12 inches. And 1 inch is 2.54 centimeters. I can do that for all 3 sides, right? If I do that for all 3 sides, I'm gonna get 12 times 2.54 is gonna be something like 30. 30.5 maybe? Who's got a calculator out?
$30.48.
30.48. Oh, not half bad. So now if I want to find the volume in cubic centimeters, now I'm gonna take 30.48 and plug it in for all 3 sides, right? So I'll get 30.48 cubed. Which I'm not gonna do that in my head. I'll try though. Is that 900 times another 30? Gonna be something in the 10,000 range. Ish. 30,000.
28,316.84.
Well, let's say we're only going to 3 sig figs. It was 28 what?
28,316.
Oh, 28.3 times 10 to the 3 cubic centimeters, 28,000, right? That works as long as we have a nice neat box and we can just convert all 3 sides of it, right? Or if we had a circle like we had in last week's lab. If you wanted the area of that circle in square inches, we just measure the diameter in inches. But if we wanted the area in centimeters, we measured the diameter in centimeters and then plugged it into pi r squared, right? What if it's not a nice neat shape? What if we want to take something like the surface area of Lake Tahoe and convert that from square miles into square kilometers? It's not a nice neat shape. We don't get to do all these conversions separately. But we can take the same approach. Does it really matter that it's a nice neat shape? Not really. If we're in cubic feet, we can go from cubic feet to cubic inches by just treating it like it's one big cube. And so if we wanted to just say, okay, I have 1 foot cubed. If I want to take that and turn it into cubic inches, I can still write a conversion that says 1 foot is 12 inches. That's still true, right? As long as the top is equal to the bottom, I'm still just multiplying by 1, which means it's fair. It's a reasonable math step. What happens if I have feet cubed on top and just feet on bottom? What do we do with units when we have units that are on top and bottom? You can think of it as subtracting the exponents. We're gonna cancel them out, right? Because just like, basically, we treat units a lot like we treat variables. If this was x cubed divided by x, we'd cancel out 1 power of x, right? It's feet cubed divided by feet, so we cancel out 1 power of feet. Right, because feet cubed is really feet times feet times feet. We're going to divide that by feet. We cancel out 1 of those, right? So that would leave us in really weird units if we did that, right? We'd be in square feet inches, which you can actually kind of make a unit that's like if you had a square foot, an inch deep would be a square footage. It's a really weird unit, but they actually measure the volume of lakes in acre feet, which is an acre a foot deep. It's a weird volume unit. We're gonna use it once and then forget that it exists because it's terrible to use. We don't really want to be in square feet inches though, right? So why don't we just do it to all three sides of the cube? Why don't we just do it 3 times? If we cube that entire conversion factor, it's still just multiplying by 1, because what's 1 cubed? 1. So we can, if this is a valid conversion factor, we can cube the entire conversion factor. And the way we distribute that means that that cube gets put inside, so it'll actually be 12 cubed feet or inches cubed over 1 cubed feet cubed. Now we have a new conversion factor. It's going to allow us to go from cubic feet to cubic inches. We don't actually need to write this onto our conversion sheet though, because all we did is we used the conversion that we know is true and we cubed it. Because we're trying to convert a cubic power of units. And we do the same thing with areas. Any higher power of units, we can do that with. And this is how we get these conversion factors that allow us to go to be have an exact conversion between metric and imperial units in volumes, is it still all comes back to 2.54 centimeters equals 1 inch. We're just going to cube it to do that. All right, so here's an example with area. If we had a box that was 1 centimeter cubed, obviously not to scale. 1 centimeter cubed versus 1 inch cubed. If we want to take 1 cubic inch and convert it into cubic centimeters, we're using that same 2.54 centimeters equals 1 inch. We're just going to square it. Because now inches squared cancels out with inches squared, and we're just left in centimeters squared. So 1 square inch is 6.45 cubic centimeters. Sorry, square centimeters. So not terribly interesting or new. It's a new way of using a tool you already have, right? And if it helps you, instead of writing it squared, you can write it as 1 inch is 2.54 centimeters. And just write it twice. 1 inch is 2.54 centimeters. That's mathematically the same. We're just converting one side of the cube and then one side of the square and then the other side of the square.
Can't you just neglect the squaring until, and then square the result?
Not always.
Oh, okay.
So in some cases, if we're going from centimeters squared to inches squared, the net result of that in this case is you could just take 2.54 and square it at the end. But if we're doing this as part of a longer conversion, that's not how exponents work. You've got to do the exponents before you multiply everything else, right?
Okay.
Remember your order of operations, right? PEMDAS, parentheses, exponents, then multiplication. All right, so let's do practice. Here's a box. What's the volume of the box? In cubic inches. This is still a case where you could convert each of these separately and then do length times width times height, or you could do length times width times height and get it in cubic centimeters and convert cubic centimeters to cubic inches. There's two approaches that should give you the same answer within sig figs. So I don't want to write the same conversion out 3 times, so I'm gonna find the volume first and then convert all the units together. So length times width times height in centimeters. I get 532 cubic centimeters. 768 and 5.56 both have 3 sig figs, so my answer, I'm only keeping 3 sig figs, right? If I want to take that and put that into cubic inches, centimeters to inches is a 1-step conversion, right? That's a pretty straightforward one. One of the first ones we did. 2.54 centimeters is 1 inch cubed. So 532 over 2.54 for the third. I get 32.5. Inches cubed. Is that a reasonable number? 500 cubic centimeters down to 32 cubic inches. It seems like a big leap, right? Because we all kind of think of a centimeter smaller than an inch, but not by much, right? But when we cube that difference, I don't know what 2.54 cubed is off the top of my head, but it's going to be about 10, roughly. So 500 divided by 10 would put me in 50. So my mental math wasn't that close because I can't cube numbers in my head that accurately. But I could get close enough to say, okay, well, maybe that actually is. Turns out volumes, when we do conversions with volumes, you get much larger differences than you might think at first because we have to cube each of these conversions. How many cubic, let's see what our next question is. Oh, gallons. Let's put that in gallons. Gallons are one of those terrible imperial units that exists for some reason, and we think in gallons, at least here in the US usually. It would be really a lot easier if everybody could just think in liters, but I can't do that for my own brain, so I'm not gonna be able to convince your brains to do that. So what is 32.5 cubic inches in gallons? Check your conversion sheet under the volume section. We've got a conversion for cubic inches to gallons, and it's an exact one. 231 cubic inches is exactly 1 gallon. So if we had 32.5 inches cubed. For every 231 inches cubed, 1 gallon. So something like 0.15 or so. It's definitely gonna be less than 1, right? Point 141. Do we need to cube this conversion though? See some people nodding their heads, some people shaking their heads. Why not?
Gallon's already kind of a cubed measurement.
It's already got cubed as part of the conversion. So because gallons to cubic inches already has cubes in it, we don't want to cube this whole conversion. Because what would that look like if we did that? One, it wouldn't cancel out properly here, but if we actually cube this, we'd have inches to the 9th power. And gallons cubed, I don't know what inches to the 9th power looks like. It doesn't seem like a real thing to me, right? I can't even think past 3 dimensions, let alone asking me to go to 9 dimensions in space. So if you get a weird looking unit, there's a possibility that you cubed something you shouldn't have. Or squared something you shouldn't have. But what's really going to help you with that is if you're in inches cubed and your conversion is already in inches cubed, then you're good. Just a regular conversion that way. All right, questions about volumes or areas? One thing I will mention here. This conversion is not explicitly written on your conversion sheet. It's one we're going to use all the time. In fact, we use it so often, sometimes I forget that it's a conversion. A cubic centimeter is a milliliter. 1-to-1, straight across. They are, I would say that they're synonyms, but even synonyms could be a little bit different. They are 100% exactly the same. 1 milliliter is 1 cubic centimeter. So oftentimes we'll see densities written in like grams per cubic centimeter, like on the quiz. That's exactly the same as saying grams per milliliter. So a lot of times, especially once you get used to doing that, that's going to be the conversion that you don't even have to show as a conversion. If you just wanted to swap that as grams per milliliter and don't even show doing a conversion, that's totally okay because they're literally the exact same thing. Anybody know another term that gets used for cubic centimeters in the medical field? CCs. CCs is short for cubic centimeters. I don't know why they don't just say mLs, because that's the same number of syllables. For whatever reason, medical field adopted CCs instead of milliliters, when they're literally the exact same thing. So CCs, cubic centimeters, milliliters, all the same. All right. If we go through this slide, then we can spend time after break doing practice, getting more familiar with conversions in our conversion sheet. So I think this is after this. Practice, 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 practice. Yeah. Good. So a lot of times in this class, we're going to deal with what I call combined units. They're also called derived units. It means that they're units that come from other units. So the most common one is speed. Speed is a combined unit because it's got a length divided by a time. Right, how far did you go per unit time? Miles per hour, right? Everybody knows what per it means, right? You had to come up with a definition. If I said, write a definition for the word per, what is that? Anybody come up with something?
The ratio?
It is a ratio.
How many of X can you fit in Y?
How many of X can you fit in Y? Yeah, the way that I break it down is for every. So miles per hour is, or in this case, meters per second is 22 meters for every second. Goes all the way back to the Latin. I think that in Latin, that is actually what its definition is for every. Which is where the word percent comes from as well. What does cent mean in Latin? 100. So percent is literally for every 100. Makes it make sense. We're gonna do a lot of stuff with percentages in this class, and that's gonna come back a lot. We're gonna use percentages as conversions a lot in this class. So in this case, meters per second. We want to convert that into kilometers per hour. How can we do that? There's two approaches to this. One is to take this is really 22.0 meters over 1 second, right? We don't usually write the one, but that's the for every piece, right? So we could take 22 meters and convert it to kilometers, couldn't we? And we can take 1 second and convert it to hours. And then just do the division. It's the most straightforward way to do it. It takes up a little bit more space, but we can say 22.0 meters every 1,000 meters is 1 kilometer. 0.0220 kilometers. Then we could say, okay, well, 1 second. And for every 3,600 seconds is 1 hour. So, or write it out if you don't have your conversion sheet with you. Everybody knows 60 seconds in a minute and 60 minutes in an hour, right? So divide by 60 and divide by 60 again is the same as dividing by 3,600. So we'll get a small number there, right? $2.7 times 10 to the minus 4. We had 3 sig figs on top, so we'll keep 3 sig figs here. Those were both really easy conversions, right? If we went this many kilometers in this many hours, to get it back into combined units, you just combine them. Take your kilometers, divide by your hours. We'll get 0.022 over, I get 79.1. In our units now still just look like kilometers over hours. We just took the number in kilometers divided by the number in hours. So our units are kilometers per hour. Nothing inherently that tricky about it. It's just another way of using the tools we already have.
So if that were, let's say 0.6 seconds at the bottom, would you only keep one significant figure for the kilometers as well?
So good question. So when we have these combined units, this top number is a measured number. So 3 sig figs in this case. if it's for every second, we're assuming this, the 3 sig figs applies to the top, and then we're treating the number on the bottom like it's exact.
Right,
So if it was a measured number on the bottom, then yeah, then that factors in. So let's say we actually found a speed by hand. We measured somebody's 100-meter dash time. And we found their 100-meter dash time, and it was 100.0 meters, and they did it in 12.2 seconds. In this case, we have 4 sig figs on top, 3 sig figs on bottom. They're both measured numbers. So when we actually do that division, put it in meters per second, we're only going to keep 3 sig figs. And then when we rewrite that, we'll still assume that that one that goes on bottom is going to be exact.
thank you.
I said that this is the straightforward way to do it, which implies there's another way to do it. There's no reason why we can't do both of these steps in the same row, why we have to treat it like it's 2 separate conversions. If we write it out as 22.0 meters over 1 second, is there anything stopping us from converting seconds into hours when it's in the denominator? Not really, it just flips everything, right? If I want to cancel out seconds, normally we're used to whatever unit we want to cancel out goes on bottom of our conversion factor, right? In this case, we want to cancel out seconds, it's already on the bottom. We want to put it on the top of our conversion factor. So we could say 60 seconds is 1 minute, or 3,600 seconds is 1 hour. It still is going to cancel out the same way, right? So now that would actually put us in meters per minute in that case. And if we did it again, we could say, okay, well, 60 minutes is 1 hour. Minutes cancels minutes again. This is going to wind up being the same net result as the way we did it before. Before we took our 1 second, we divided by 3,600, and then we took that number and we put it in the denominator. So we divided by that really small number we got, right? Instead of dividing by seconds, we're going to just multiply it. We just flipped the reciprocal twice, mathematically. All you really need to do to track your units on this though is what cancels out. That would put us in meters per hour if we did it that way. And then if we wanted to then turn it into kilometers per hour, yeah, we have this in the way now, but if we ignore this, we still want to convert meters to kilometers. So we can still say 1,000 meters is 1 kilometer. Do they have to be directly adjacent to each other for the units to cancel out? No, that's one of those properties of multiplication. It doesn't matter what order we put these in. Mathematically, everything's going to come out the same, right? So I'm canceling that meter with that meter. But when we look at our final result, we're still going to get kilometers on top and we're still going to get hours on bottom. So any of these combined units when you want to convert a combined unit, you can split it up into 2 pieces and do it as 2 separate conversions and then put them back together at the end, like we did the first time. Or you can do it this way, mathematically identical. Depending on the rounding, you might be off by 1 in that last sig fig, but that's why we have sig fig rules, right? All right. And then if you actually run it all the way out, in this case, it didn't make a difference where we rounded. They wound up being the same. Depending on the exact numbers, they might round a little bit differently if you did it in 2 separate steps, the way we did first, versus doing it all at once. This is just showing the work I just did on the board a second ago. Let's do a practice and then we'll take a break. Let's convert. I already mentioned I'm a baseball fan. It's almost baseball season again. Pitchers and catchers report in 2 weeks. So spring training is almost here. The pitcher shows back up and he's throwing his 93-mile-an-hour fastball. What is that in meters per second? Miles per hour is all well and good, but if you actually want to know how fast it's going, meters and seconds makes more sense for a baseball, really, right? So somebody asked me on the test, on the quiz, if there are any conversions that you need to memorize for this class. For this class, no. I'm not, now that you have this conversion sheet, I'm never gonna take this conversion sheet away from you. I might make you use a fresh one if you've taken notes all over yours and we're doing a quiz or something like that. But in general, you will always have your conversion sheet, so there's no need to memorize anything. You might still wind up memorizing things just because you use them all the time. So there's a faster conversion we could have used to go from miles to kilometers, especially since we only have 2 sig figs, right? We only have 2 sig figs, you can use that 1.609 kilometers equals 1 mile. These are the ones that I have memorized though. So even though it's more steps, I didn't have to pick up a piece of paper and look it up. I have both memorized at this point, but this also, if we event, all of these are exact. This is a better number, even though it's going to give us the same number. We're gonna get 3,600 seconds on bottom. And I get 1.50 times 10 to the 5th meters. On top. So put it in meters per second, take that number, divide by that number. Should get something around the 48 region, I want to say. 41. 42 after wrap. A good number. It's interesting to think about pitch speed in terms of meters per second. Because 42 meters is close to 50 yards, right? So basically this baseball is moving fast enough it travels half of the football field in a second. And if you actually look at the amount of time it takes to go from the pitcher's hand, this is just me geeking out about baseball, this is not a test. If you look at the amount of time it takes at baseball to go from the pitcher's hands to crossing home plate, your brain actually doesn't refresh your vision fast enough to get more than 2 frames. You get 1 frame as it's leaving the pitcher's hand, you get 1 frame when it's halfway to you, and the next frame it's in the catcher's mitt. Which is wild when you think about the reaction times of pro baseball players and how fast they have to make that decision about whether to swing or not and where it's going to be. Leads to a lot of fascinating psychology research actually. Because do I have any big baseball fans in here? Played for a while. What do they say about a 4-seam fastball? What does it do? How does it move? It goes pretty straight. So at the MLB level, they'll say it rises, which is actually physically impossible. It can't rise. But what happens is those 2 frames, it turns out it just doesn't drop as fast as your brain expects it to. So when you take a swing and you're underneath it, your brain says, well, it was supposed to be right here. I put the bat right here. Why didn't I hit it? Your brain goes back and corrects your memory to say it must have been gone up from where it was supposed to be. So your brain perceives it as rising, even though physically it doesn't rise. A lot of weird stuff happens when you push your brain right to the limit of what it's capable of. All right, let's take a break. Let's come back at 11:30 and we'll do some more practice with these.
One, two.
Yeah, Chris.
I'm gonna get the top number.
When I plug in 93 times 5,280 times 12, when you go this one all the way across, gives that.
Oh.
Yeah, sorry, while I still have people, there was somebody in here who was in the Monday lab that wanted to change to Wednesday. That sounding ring any bells? All right, come on up here. As you were, back to break. Yeah. Write down your name. Don't write it on that because I want you. There, write it on. Write down your name and your ID number, and I can go take care of this after. You wanted to go from Monday to Wednesday, right? Perfect. We can just do a 1 across the spot. Just write name and ID number there, and then write down Wednesday to Monday. So I don't mix anything up. You want to go Monday to Wednesday. You want to go Wednesday to Monday. Perfect. See, this is why you need to write it down for me.
What is on the elements coming up here?
Does that have a date on it on Canvas? Cause I'm, that's a moving target. We'll set the date. I'll give you at least a week notice, but when we start talking about the periodic table, yeah, there will be one. Okay. Yeah.
Yeah.
So just because, what is 10 squared?
You don't know your number yet.
No, that's 10 times 2. 10 squared is 100. So just because I know there's 100 centimeters in a meter. So right there, right? So I just, it takes up less room if I write 10 squared than if I write 100. So I just do that shorthand. that make sense?
Cool.
Levi, yeah,
Still can register because of the special call.
so I'm gonna get everybody who's still waitlisted, because there's a few of you that also bring in the issues. So we're gonna go down to student services all together after this, and I'm gonna get everybody registered so we can be done with this and get
Sounds good.
you access.
Okay, sounds good. Thank you.
Thank you.
It's not like he's been checking.
Cool. Then I'm gonna go talk to them about this. I'll probably go down after class, but we'll get it all sorted and get you switched across.
Okay, thank
Yeah.
you.
Thank you.
It's so weird. I'm saying. So it was good home for hours. They got the class. My body's touching. I tried to make myself look well, and then like I couldn't sleep last night. I took a shower so that I can lay home late afternoon. And I was like, I'm gonna take a shower, then take my phone. Going to bed and I'm tossing and turning for like an hour now. It was on the freaking night, you have to get early to yeah. And so I just stood because I took a sleep and then I fell asleep at like 4 in the morning. I can't fall asleep. I'm like, never my husband like that for like 2 hours, just like yeah, I went to that. Wait, she said, and I was like, further like 5 year old. And like it's price. I would when I said like pills and stuff like it just doesn't work. I left a little bit earlier. It's been hard to do, you know, you're actually kind of very. Oh. Where is it just? I don't know. If I had a thousand feet. She's probably telling Jeremy she's still sleeping. That's fine. That is always out there. My mom. You should. My mom says that you should start taking melatonin. My mom says you should start taking melatonin. Like, oh, this is clear. I like having the clearness because I like showing. I want to start getting into the color cases and things. I just don't know like what to put these. Did you get the pro? Sorry for the late start, but. Oh, no. Hello? This was so late.
That's a good one to do next, because we're talking about combined units, right? So yes, when everybody comes back in here, we'll talk about that. Hopefully make it make more sense.
Can you?
Oh, you mean on
Yeah.
yes, okay, let's do that one right now then.
I was thinking of getting. Yeah. There's this clear BD pin, and it's like clear.
So because we've got this mega, in mega is 10 to the 6, so 1 megameter is 10 to the 6 meters. So we're gonna use that 1 megameter 10⁶ meters, because the megameters are big to big, right? So if we wanna go from meters to feet, we know how to go from meters to feet, we just need to get to meters first, right?
That's what I'm saying, like.
Cause once we get, if we're planning this out, we can go megameters. We get to meters, we can go to centimeters, centimeters to inches. Inches to feet. So I know I did that really fast, but if we look at our conversion sheet, there's, yeah, we've got a conversion for. This is the one that's not explicitly on there either, right? That's another prefix. But that's a common one that we use all the time. Centi means 100. Right, it takes 100 centimeters to make a meter. And that one's on here too. It's okay. You just missed that one. Okay, no worries, that's an easy fix. We work it out the rest of the way anyway. Go megameters.
Yeah.
1 megameter is 10⁶ meters.
Okay.
1 meter, 100 centimeters.
Oh, yeah.
Centimeters, inches.
Yeah.
And then 12 inches.
So it's like, I'll just listen to my that's quiz and I was on 20 hours.
Yeah, I was like, not 20 minutes, I was like, but I didn't know the exercise.
This was all right. And I was like, oh. I had to redo it.
I was like, wait till like the first one.
I started the quiz at work on my computer and I didn't have a way of uploading anything. So my time on the quiz is like over 10,000 minutes, cause I waited until I got
That's
home.
totally fine,
Yeah,
that's
it's funny.
You wanna do it a little bit at a time, if you wanna come back to it, think about it, leave it open, whatever, that's all totally fine.
That's why I started it at work, but I was like, well, you know, worst case scenario.
No problem with that, and I see that more students do that than not, they'll start it on Friday afternoon, and go back to it, finish out. That's fine.
I don't know.
Okay, that's good, that's easy.
I'm testing it.
Fast. And I don't, and make no promises, because it's easy to get stressed out.
You have the center thing on.
You jump over that.
I did. I don't remember how.
I was looking at my phone for like.
But I was invited. Yeah, there was a.
I was like.
Must be good enough for everybody else.
That's a good one.
Listen, Jackie. We'll deal with your pieces with it.
All right, as promised, let's do some practice. Let's say I drove someplace that is not like Tahoe, so that these prices make more sense.
Oh, my.
And I got a gasoline price. $3.259 per gallon. I want to convert that into euros per liter. How can we do that? Do that exact.
Well, that's fine. Thank you. No, it's cool.
Another combined units one. We want dollars per gallon into euros per liter. Obviously, I have to give you more information on this one because you don't have a standard conversion for dollars to euros. Since that changes all the time, right? Well, let's just assume that this number is still good. With these combined units, if you're not seeing a way to do it easily when they're put together, if it looks intimidating when it's written as dollars per gallon, and you're not sure what to do, break it up into two conversions. Convert your dollars to euros, and convert gallons to liters. This one uses all the new tricks, right? Combine units and one of them has a volume involved that we had to cube. So the dollars to euros, it's not a conversion we've seen before. But as long as I tell you what that conversion is, doesn't really matter what the number is or that it's different. Currency is just a unit like anything else. So do a conversion like anything else. Do sig figs apply to currency?
I would look for conversion.
You would think so.
Cause I know banks round, but
Banks on gas stations too. Gas stations charge you $3.25 and 9/10 of a penny. Right? They're keeping track of that 9/10 of a penny. So that means that these are all four sig figs. Is this a measured or an exact conversion? Does it change? Measured. It's about $1.09 in the euro. Not exact. If it was defined that way, there are actually a couple of currencies in the world that are actually exactly tied to the dollar. I want to say dollars in Panamanian dollars are defined as being exactly the same as a US dollar. That's an exact conversion then. But for any of these other ones that can change, that's a measured number. That means we need to pay attention to sig figs. So we get, what, if we round this to 3 sig figs? 2.99. Then up at the top. 1 gallon is 231 cubic inches times 2.54 cubed.
That's okay.
Over 1,000.
Is this, does it include a cube?
How many sig figs should we keep here? We kept 3 here. If we really wanted to, we could keep 1 extra since we assumed that that 1 gallon was exact. We only used exact conversions. You could keep 1 extra. But it shouldn't really make a difference if we're following our rules everywhere else. So 3.79 liters.
Basically, then I know. What is being counted inside? It's not that true.
Several of you don't seem convinced. Or you look like you're puzzled where to go next.
What I'm just curious about is that if you're doing like the,
No,
I don't know what to call it, the mixed conversions, where you're really going at the same time. Can you keep track of what kind of unit would be on top of the end?
But the brick piece.
That makes
So
sense.
So if we wrote this the other way, it would be over gallons here, right? If we just did that, we'd get a price in euros per gallon. And then we would keep going. These conversions would all be flipped. They'd be tied onto the end. Well,
Okay, so you don't necessarily impact the
Exactly.
unit time to the end result at that point.
it's still gonna be a currency divided by a volume.
Right, it's just that it's done as part of the process, you just assume, okay, well, not assume, but.
Well, if you actually look at. If we look at what we get there, so dollars per gallon. Dollars to euro. And then on the other side, it was gallons, inches cubed, centimeters cubed. Gonna be centimeters cubed, liters.
Yeah.
So it's still, so those cancel out, so we're in euros, but then it's still gallons cancels gallons, inches cubed cancels inches cubed. We're just canceling from the bottom to the top instead of top to the bottom.
Right, that makes sense.
Yeah, no problem.
Measure.
Then our final answer, put it in euros per liter. We take our number in euros, we divide by our number in liters. We should get something a little under 1. Point 789. See, how do you draw the euro symbol? Is it like that, I think? Currency symbols are weird. I really don't like when you're supposed to put them in front of the numbers either, so I'll usually write them like this. All right, questions? Anybody get lost along the way? Yeah, Levi?
So I went gallons to quarts to liters.
Yeah,
So, and my answer turned out 0.790.
790.
Yeah,
That's what I got for doing it all in the same time.
Right, so this is perfect. This is a great example of one where if you didn't stop in the middle of the round, you got a very slightly different number, or if you used a different conversion, you got a very slightly different number based on the rounding. If I'm looking at those two numbers, 0.790 versus 0.789. That's only off by one in that last digit, right? That's the whole point of sig figs, is to show us where our uncertainty is. So that's fine. Which is also, I also forgot to mention this last week before you took your first graded quiz. Canvas's auto grader is terrible. And it doesn't allow me to set up the auto grader to work in a way that handles both sig figs and gives accounts for like that uncertainty in the last spot. So a number of you, probably half of you, got 926 instead of 925 kilometers on 2 tanks of gas. That's still a full credit answer. It's the same answer within sig figs, right? Except for the fact it's also exactly what ChatGPT throws out when you put that problem in there. So that's not strong enough evidence. I would accuse anybody of using ChatGPT because you can get 926 by rounding in other ways, but you round in standard ways, you shouldn't have gotten 926. Just saying. Anyway, it's still a full credit answer though, because it's within one sig fig. I can't set up Canvas's auto grader to do that. So anytime you turn in a quiz, even if it has auto graded portions, I always go back through on Monday or Tuesday of the next week and give partial credit where applicable and full credit where applicable. So most of them. But kudos to you all. This is the first time I've ever had a class of this size that didn't send me panicked emails when 926 got marked down for 0 points. Saying, but I got 0 points. Is there any way I can get partial credit? I usually get at least 3 of those on the first quiz. And y'all didn't do that. So good job. Let's do a density problem. Anybody have their work from the last problem on the quiz still up? I don't want to bother logging into Canvas right now, but I want to do that same problem. Go the way that I would write it. It was 12 point something. 12.24 grams, right? And the density was.
It's funny.
Is that is there a truck outside backing up or something? What is that? Backing up. Right. Door open. Let's see if that helps. I don't know what they're backing me, but all right. So this problem, this is another way we can use these combined units. Instead of just converting combined units, I could ask you a similar question with a density instead of a speed. Where I said something like, okay, this 2.25 grams per cubic centimeter, what is that in pounds per gallon? But let's talk about the problem instead. It said, okay, you got, was it graphite?
Yeah.
12.24 grams of graphite. And I want to know, based on this density, how many cubic centimeters that is. So you can write that as an algebra problem, where you go check your equation sheet, you see density is mass over volume. You can plug in the mass and you can plug in the density and solve for volume. That works perfectly fine. I tend to think about these combined units as conversions though. The easier way to do it that involves no algebra is if you just realize grams per cubic centimeter is a conversion. Just like you can use speed as a conversion. Just like if I said, okay, I'm gonna drive for 4 hours at 65 miles per hour. Man, that would be slow. I can write that 65 miles per hour as a conversion, right? I can say, okay, 4 hours for every 1 hour, that's 65 miles. 65 miles over 1 hour is a conversion. Because it's saying under these conditions, 1 hour is equal to 65 miles. And then if you watch the units, hours cancels hours, we're left in miles, just like you would all do this intuitively, right? If I just said, how far did you go in 4 hours? You've all been doing that since you were in probably 7th grade when you first learned about word problems, right? It's a little trickier to see with a density, but densities don't doing the exact same thing. Density is a mass per volume. So it's saying if you have 1 cubic centimeter of graphite, that's 2.25 grams. So that's a conversion too. Anytime I ask questions like this, I get a lot of people will ask questions, say things like, well, do I divide by the density or do I multiply by the density? I don't know, whatever makes the units work out. You look at it and say, okay, if I've got grams and I want to cancel out grams to be left in cubic centimeters, I'm going to use this as a conversion. That was the wrong button. 12.254 grams. And for every 2.44 grams is 1 cubic centimeter. Anytime you get a combined unit, you don't need an equation for it to convert between those variables. All you need to do is treat it like a conversion. So grams cancels grams, we're left in cubic centimeters, and we get 5.44. A lot of fours in there.
2.25.
2.25.
Oh, well, yeah, the other one.
Oh, 2.25, there it is. Now it's just sloppy.
Right.
So you can do it the other way. Especially if you have your conversion sheet or you have the equation for density memorized. Density is mass over volume. You can do it the algebra way. You'll get the same exact answer. Just, I really like conversions as a way to solve word problems. So I always look for ways to do this instead. Because then I don't have to stop. Because what if it's part of a larger conversion too? What if I actually had pounds and then I had to get it to grams and then I could take grams and plug it into the density equation and solve for it. And then I'm supposed to start another conversion on the other side. If it's really all just conversions when you actually write it out that way. Anytime you have two things that are equal to each other, it's a conversion. Right? They don't have to be the same type of unit. Are speeds measured or exact?
Relative to something.
Yeah, usually, well. Let's see, relative something. If you make it into a velocity, but now we're getting into physics. The difference between speed and velocity is really a physics issue. But yeah, so we're in general, when we talk about speeds, we're talking about relative to the surface of the earth. Treating the surface of the earth as though it's stationary. But again, now we're getting into physics. The point I was trying to make is that speeds are measured. They're not exact. Are densities measured or exact? Measured. Even the one that seems like it could be exact, which is 1 gram of water is equal to 1 milliliter. That's not exact either. It turns out these densities actually change based on temperature. Solids don't stay the same density when you change the temperature, they expand and contract. So if they expand and contract with temperature, like you guys have probably heard stories about how the Golden Gate Bridge gets longer in the summer because the temperature is warmer. Actually, by a fairly measurable, not something like 10 feet. The Golden Gate Bridge gets 10 feet longer in the summer because the steel expands in the summer. But that if it's expanding, that also means that it's not a constant density. It means the density of that steel is dependent on the temperature. So anytime, just like with the currencies, anytime you got something that can change, or something where adding more decimal places would make it more accurate, it's a measured number. What about, what are some other good examples? What about pi? Pi a measured number?
Yes.
Why?
It's,
There's more digits, right? In fact, there's infinite digits. You could never actually use an exact value for pi in anything because you would have to spend an infinite amount of time typing in an infinite number of decimals into your calculator. So pi is measured. But it's also weird because it's one of those fundamental constants of the universe, and yet it's a measured number. But turns out that's the world we live in. It's irrational numbers are weird. You even call them irrational. All right, let's do a fun one. Who's seen Indiana Jones and the Raiders of the Lost Ark? That is way too few hands. All of you need to watch Indiana Jones and the Raiders of the Lost Ark. Everybody remembers the scene at the beginning, the big rolling boulder, right? Grabs the idol, stuffs it in his man purse and books it. How much would that idol have weighed if it was solid gold? How big was the idol? We're gonna guess, we're gonna estimate. Roughly head sized ish, about that size. Call it. Let's just say it was a sphere. We do this a lot in physics. We just assume things are spheres because it makes the math easier sometimes. Let's assume it's a sphere. And it has a radius of, let's call it, I don't know, 8 inches. 8. That's I have a fairly large head and I wear a 7 3/4 baseball cap, so it's 8 inches is a decent estimate for the radius of somebody's head. Or for the diameter.
I was gonna say Brady, huge.
So the diameter equals 8. So if our diameter equals 8, what's the volume of that sphere? Check your conversion sheet. Your conversion sheet has geometric equations on it too. We're close.
Oh.
So if we want to know the volume of that, we're estimating its diameter of 8. So radius equals, call it 4 inches. This is a really rough estimate. So we're gonna give it 2 sig figs just for the sake of the calculations, but really we know it's probably plus or minus an inch. But that doesn't make the calculations make much sense. In a second, we'll wind up rounding too much. So we can get the volume of that solid gold statue. So all we have to do is plug in 4/3 pi 4.0 cubed, that's in inches. We're gonna get a number in cubic inches then, right? So this is an example of what we call in the sciences a back of the envelope calculation. the point of back the envelope calculation is not to have as many statements as possible. It's basically a way to do like a reasonableness check. What would be a reasonable guess for these numbers? We had to make a guess about the size, right? If we're gonna try and figure out how much that idol weighs, we're gonna start by figuring out how big it is. What do we get for the number?
260s, well, I guess 27 million times 10 to the first, right?
Okay, 27, 2.70. 270, you said?
Yeah.
So this also brings up another thing that happened on the quiz. It's worth thinking about. Scientific notation always has one digit to the left of the decimal point. Several of you made it so that your scientific notation only had one number to the right of the decimal point. It made it look more complicated than it needed to, at least if you're used to scientific notations. We want one digit to the left of the decimal point to actually put it in scientific notation.
I'm using all of that right here.
4/3 times pi times 4 cubed. So you're gonna cube the 4 first, then times it by pi, times it by 4/3. So we have a volume estimate. If we wanna know how much that object weighs, and all we have is a volume, we can use the density to do that. Because density is how you convert between masses and volumes. Put this in the category of more random numbers you don't need to memorize because you can always look them up. But I've been doing this for a bit, so I happen to know the density of gold off the top of my head. If you didn't know it, you just look it up. From a reputable source, don't just give whatever AI overview Google spits out because it's wrong more often than it's right. You can't, it's hard, it's a rough world we live in. The density of gold is 19.3 grams per cubic centimeter. That seems, I guess, like a reasonable number, right? You don't have any context, it's hard to visualize. Probably very few of you have held a 1 centimeter cubed brick of gold in your hand. And 19 grams, probably don't have much of an idea what that looks like or feels like either. So you don't really have a way to do a reasonableness check on me on this one. But believe me when I say that's high. Density of water is 1 gram per cubic meal, blah, blah, blah. 1 gram per cubic centimeter per milliliter. So what do we get? How do we figure out what that golden idol weighs? We've got cubic inches. We can convert cubic inches to cubic centimeters, right? And then once we're in cubic centimeters, we can use the density to get grams. And just because most of us think in terms of pounds, we'll then convert grams into pounds. All right, so there's our plan. Inches cubed, centimeters cubed, grams to pounds. It's that simple, right? There's nothing to it. No, I get that there's more to each of those steps, but even if each of these steps is something we have to stop and think about, we know we can go cubic inches to cubic centimeters. We've done that already today. And once we get to cubic centimeters, we can use the density to get to grams. We did that once already today too, on the quiz. And so sometimes the trick with these longer problems is to break it up into steps that you know how to do. Right? Don't get bogged down in trying to, how the heck am I going from cubic inches to pounds? I don't know any of that. If you can break it up into steps, even if each step is its own problem, that still gives you a way to get there. On the final exam, question 10, so the way the test is written, it's 10 parts. Each part is worth 10 points. Total of 100 points. The last part is gonna be a wild card question. It's gonna be some sort of word problem. Most of them, the first 90 points, you're gonna know exactly what's on there. I'm gonna tell you exactly what's on the test. All I'm gonna do is switch out what the chemicals are, what the numbers are, but it's gonna be the same exact problems for the first 90 points. And then the 10th problem, I'm gonna ask you to do a little word problem. And think on your feet a little bit. If this was question 10, just writing this, you got just to where we are right here, that's probably a 6 out of 10 at least. Finalizing everything, getting all the way to your final answer is how you get a 10 out of 10, but having a plan for getting there is half of it. This is showing getting there and you've started to actually get the number. Right, so I don't expect you to be able to do this in a timed test situation other than that one time. I'm gonna make you think on your feet. Other than that, if I ask problems like this, it's always in a group work setting or in a lab where we have time and we can check sources and things like that. Right, so don't panic because this seems like it's a huge problem. It is a big problem, but we're working together, okay? All right, how do we go from inches to cubic centimeters? Cubic inches to cubic centimeters. At 2.54, and we've got to do it how many times? 3 times, 1 inch. 2.54 centimeters cubed. We've got to do it 3 times to account for all 3 dimensions. And then we're in cubic centimeters, so we can use our density. We can say 1 cubic centimeter equal to 19.3 grams. And then how do we go from grams to pounds? Yeah, we check our conversion sheet, 453.59. 453.59 grams, 1 pound. What do we get for a number? Yeah, 188, 190 pounds. $270 times 2.54 cubed times 19. Yeah, and if we're gonna call it 2 sig figs, we'll round it to 190, so plus or minus 10 pounds. Indy's awfully athletic to be able to throw a 200-pound solid gold object into his satchel and run and jump across pits and outrun a rolling boulder. And I choose to believe that that's not due to oversight on Steven Spielberg's part. I think it's really just that it's not a solid Bible, so we're gonna go with it. Sorry, Torben.
No, I'm just having trouble finding the grams to centimeters on the version chart.
Under mass. The first one under mass, grams to pounds. What were you looking for?
Grams to centimeters.
Oh, so because that's gonna be different for every substance. Every substance has its own
Yeah.
density. So on a more detailed periodic table, a lot of periodic tables will have the density of all the pure substances written. But even that's not complete, because as soon as you have a compound or an alloy or something like that, it's you're gonna have to go look up a density. Stainless steel has a different density than iron, even though they're made mostly of the same stuff.
That makes sense. Pretty cool, so you can just, I like the little treating it as a conversion thing.
It's,
Well,
this is one of the reasons why I really hammer conversions, is because this seemed like a pretty tricky problem. If I just said, here's a picture of a golden idol, how much does it weigh? That'd be part of what this class is teaching you how to use the tools you have. And one of the biggest ones is gonna be conversions and thinking about units. Being able to make an estimate helps as well. Coming up with that number was the only thing we really made up. We didn't really make it up. We're just going off memory. For the record, if you need more incentive to watch Raiders of the Lost Ark, Steven Spielberg has said that the opening scene to Raiders of the Lost Ark is the only piece of cinema he's ever made that he is actually convinced is perfect. He is happy 100% with the opening scene of Raiders of the Lost Ark. And he can't even say that about Schindler's List. About his own, I'm just referring to his own work. He loves that movie with good reason. It's cinematic treasure. And I believe it's on Disney Plus. I think things are on Disney Plus. The rest of the Indiana Joneses you don't really need to worry about. First one, worth it. All right. Yeah, this is a weird time slot. We still have another 15 minutes. Let's do a simple one for practice.
No, I'm really.
So, ethanol. Who knows what ethanol is? Alcohol, drinking alcohol specifically. There's a lot of compounds that are called alcohols. When you take OChem with me in 2 years, we'll go over them. They are almost all pretty poisonous. Ethanol is the one small alcohol molecule that we can ingest without immediately dying or going blind. So any other alcohols, do not ever ingest them. Both rubbing alcohol and methanol, which is camp stove fuel, that's also an alcohol. They will make you go blind and then permanently, and then you die very quickly. If you're lucky enough that you only go blind, then that means that you're very lucky. So ethanol is the only one that you can drink. Even that's not really healthy for you because it's just much slower at killing you. But if ethanol has a density of 0.79 grams per milliliter, how many grams are in 45 milliliters of pure ethanol? Different numbers, and it's ethanol and not graphite, but this is the exact same problem from the quiz, really, right? Except I give you the volume instead of the mass. That doesn't really matter, just make the units work out. So we're gonna get something in the 38 range. And so this is why people ask me, oh, am I supposed to multiply by the density or divide by the density? I don't know, make the units work. I started with milliliters, I want milliliters to cancel out, so I put milliliters on bottom. Does it really matter if I'm multiplying by the density or dividing by the density, as long as the units work out? Again, you can do this the other way. Density is mass over volume, plug in density. And plug in volume. Solve for mass. Mathematically, you get the exact same thing. You're multiplying the two numbers together. This is just how my brain works. And I think it's a more powerful tool. There's more, but I think that they always, because this is a Monday, Wednesday class and we have all these Monday holidays in the winter quarter, they scheduled 10 extra minutes. But I think when you hit 2 hours, I think that's a good time for a lecture. I think we could probably call it. All right, if you're still waitlisted or if you have other student services issues that you need my help with, hang around. We're gonna go down to student services and get all that taken care of. The waitlist students or anybody else who needs it. Times a million, times 100, divided by 4, divided by 12.
Hey, so I'm talking. No,